We'll have a look at the challenging optimization problem. I'd like to encourage you to really wrap your head around this. I'm just going to show how it's solved, but please try and understand every detail of it, okay? The question is quite simple. We have two corridors, one a wide one with 2 meters, and then at a right angle it narrows down to 1 meter. Okay? The question is, what is the longest ladder that you can walk around that corner? Well, this problem translates into a slightly different question. The question could also be formulated, what is the shortest line segment you can draw within this corner? Okay? The shortest line segment you can draw is going to be the longest ladder that will really pass around the corner. Now, let's compute that. We introduce right angle triangles here and there. Of course, if you absolutely want to, you can try this yourself and pause the video. It is going to be challenging though. This is 1, this is 2. Let's call this length 1 and this length 2. And let us also introduce an angle. We need to be able to describe these different line segments, and they can clearly be described by the angle we have here. I'll call this angle phi. Alright, now let's try and express everything in terms of phi. In the first triangle containing L1, we can use a cosine. The cosine of phi equals adjacent leg over hypotenuse L1. And in the second triangle, we can use the sine of phi. The sine of phi is opposite leg 1 over hypotenuse L2. Therefore, we can rearrange this. L1 is 2 over cosine phi, and L2 is 1 over sine phi. So what we get for the total length, depending on the angle phi, is 2 over cosine phi plus 1 over sine phi. That's a formula for the length of the line segment depending on our choice of the angle phi. Now we want phi determined in such a way that L becomes as small, as short as possible. This is going to correspond to the longest ladder we get around the corner. So obviously we need to compute the derivative of L of phi. It's perhaps a good idea to slightly rewrite this. This is 2 times the cosine of phi to the negative 1 plus the sine of phi to the negative 1. You could also have used quotient rule naturally, however I prefer chain rule and rewriting this as a power with a negative exponent. We can now compute L dash of phi. This is 2 times the derivative of cosine to the negative 1. So chain rule tells us that this is negative 1 times the cosine of phi to the negative 2, lowering the exponent by 1, and multiplying by the inner derivative, so the derivative of cosine, which is negative sine of phi. Plus, the same back here, sine to the negative 1 differentiated becomes negative 1 times sine of phi to the negative 2 times the derivative of sine of phi, which is cosine of phi. This can be rewritten, first of all, minus 1 times minus 1. We have in the numerator 2 times the sine of phi, these two terms, and this cosine to the negative 2 can be rewritten in the denominator. It is just cosine squared of phi. A reminder, you haven't seen that a lot, but cosine all squared is usually written as cosine squared of phi. Back here we get minus cosine phi over sine squared phi. This is the derivative, and this is what needs to be 0 if we expect a maximum. Naturally, we get rid of all the fractions. We multiply by both cosine squared phi and sine squared phi. What we get is 2 times the sine cubed of phi minus cosine cubed of phi equals 0. Now we do a nice trick. We divide everything by the cosine cubed of phi. What we get is 2 times sine cubed phi cosine cubed phi minus 1 equals 0. Or we could also write this as, because it is the same exponent, it is sine of phi over cosine of phi all cubed. And this needs to be, well, 1 over 2, right? Now I hope you remember the expression here. Can be replaced by tangent of phi. So tangent of phi is 1 over 2. They're cubed, of course, sorry. So tangent all cubed is 1/2, which lets us believe the tangent of phi is the cube root of 1/2, and phi therefore is the arctangent of the cube root of 1/2. Isn't that a nice answer? That's the exact value. If I type this in, I get the arctangent of 0.5 to the 1/3. Oops, that was incorrect, unfortunately. 1/3. So what we get is this is approximately equal to 38.44 degrees. Let's have a look at what this actually means. It's the phi that we found. Phi is the value here. What we are actually interested in, of course, is the length of the longest ladder that fits around this corner with corridors 1 and 2 meters wide. So let's just plug this in. 2 over cosine phi over cosine phi plus 1 over sine phi. If I store the angle I've just computed in my calculator and compute to this expression here, what I get is L is approximately 4.16 meters. Okay? That's the longest ladder that fits around that corner. I think that hasn't been entirely trivial. So if you haven't understood everything, please walk through the video again and try to get it, okay? This part here is one of the reasons why I showed this video and why I actually solved this optimization problem is what I meant, okay?